Hi class, welcome to exercise 5A, expanding expressions, and welcome to our new unit, quadratics and parabolas. In today's lesson, our examples in pre-learning will be example 1, expand simple expressions. And your pre-learning for this example will be questions 1, 2 and 3 in the new book and questions 4 and 5 in the old book. And then we'll do example 2, expanding binomial products, perfect squares and difference of squares. And your pre-learning for this example will be questions 4 and 5 in the new book and questions 6 and 7 in the old book. And then finally we'll do example 3, which is expanding more binomial products. And your pre-learning for this example is 6, 8 and 9 in the new book and 8, 10, 11 in the old book. So this unit will begin like most units do, with a lesson that is almost 100% revision. But it is a very important warm-up to new methods of factorising. And also, I should say, it's a great welcome back to algebra. So strap yourself in, get ready for the ride, and I'll see you in the introduction. You are already comfortable expanding algebra expressions, like b times x plus a. We just multiplied both elements inside the brackets with b. And so we now have bx plus ba, and we found this by using the distributive law. And a number version of this would be 6 times 10 plus 2, where we would multiply both the 10 and the 2 by 6, which gives us 60 plus 12, which is equal to 72. Now we do this mental shortcut all the time to multiply 12 because 10 plus 2 is equal to 12, and so we now know that 6 times 12 is 72. I'm sure you already know that with your times tables. We're going to move beyond that and look at expanding two binomial products. To do this, we're going to have to extend what we know about the distributive law with the product of these two binomials. So the first step is we multiply each element in the second binomial, or the one on the right, by the binomial on the left. Then we can expand the binomial on the left, and then by collecting like terms, we end up with x squared plus b plus a times x plus b times a, because these are the like terms. Now this obviously is the algebra version, but there's also an analogy with numbers for this. Now 18 times 12 is actually 10 plus 8 times 10 plus 2. And to prove it doesn't matter which side I do it with, I'm going to expand the bracket on the left first, and then the one on the right. And once we figure out these multiplications, we're left with 100 plus 20 plus 80 plus 16, which is equal to 216. And once again, this represents a mental trick that we all do all the time. Now, because this is revision, you should be pretty comfortable with this. However, you must be careful with positive and negative signs and what is multiplication or addition. So one method a lot of people use to step through this is called FOIL, which stands for first, outside, inside, and last. So let me demonstrate that with this product of binomials, where first is a multiplication of the two first elements, outside is a multiplication of the two outside elements, inside is a multiplication of the two inside elements, and no surprises for guessing, outside is the multiplication of the two outside elements. So let's compare what we've done here with some binomials that include negative and positive signs. So we have these two binomials where there is a negative sign in both of them, and implementing FOIL on this, but taking into account the negative signs, which I've left in their brackets now for obvious reasons. Now, taking all that into account, we end up with x squared minus ax minus bx plus ab. And then once we collect like terms, we're left with x squared minus a and bx plus ab. Now I've left a and b as positive because they're inside brackets with the minus sign on the outside, which does make them all negative. And collecting like terms in this way might look a little complicated, but rest assured, when we start doing our problems, a and b will most likely be numbers, and that should make a lot more sense with you at that point. But just for now, this is obviously some theory for you to refer to if you ever get confused. And I want to do one more example with one positive sign and one negative sign, and performing FOIL again, taking into account the negative signs, leaves us with x squared plus a minus bx minus ab. Alright, there's another way of looking at these binomial products, and some people find it easy to see them as areas. So let's imagine a rectangle that has one side that's x plus a long, and another side that's x plus b long. Because the area is equal to width times length, we can see the width is equal to x plus a times x plus b. We can break this rectangle up into smaller squares and rectangles. So because this side length here is x and this width is x, if we form a square with these sides, the area inside must be x squared. And then underneath that, we've got a rectangle that has a width of x and a length of b. So clearly its area is x times b. And then another rectangle with one side length a and the other side length x. And finally one that's a times b. And it's pretty obvious that the binomial product is equal to x squared plus b plus ax plus ab. At some point you might be able to take the shortcut and skip the FOIL here and just write out the b plus ax and the a times b. Well, hopefully you get confident soon enough. Anyhow, with certain types of binomial products, we do have shortcuts. One of these is when we have what's called a perfect square, i.e. some number x plus b squared will equal x plus b times x plus b. So then expanding that by using FOIL and then collecting like terms, and considering b plus b is 2b, we end up with x squared plus 2bx plus b squared. Therefore, you should know that x plus b squared will always equal x plus 2bx plus b squared. Now you should be able to do this without FOIL. And the other special binomial product is what we call the difference of perfect squares, which we'll now call D.O.P.S. And that's because we're going to use it a lot in this unit, so you better get used to this acronym. So this comes about when we have a binomial product like x plus b times x minus b. So notice that the first element of both binomials is the same, and so is the second element, but in between them we have the opposite sign. So when we use FOIL, we end up with x squared minus xb plus bx minus b squared, which is just a natural consequence of multiplying minus and positive. But this minus bx and plus bx actually cancel each other out. So when you take that into account, what we're left with is x squared minus b squared. So therefore, you can take it to the bank that x plus b times x minus b is going to always equal x squared minus b squared. And you can do this without FOIL. And I should also point out that it's a two-way relationship for both the difference of perfect squares and perfect squares. In other words, if you see it in that expanded form, you could rewrite it in the factorised form if you wanted to. Now, to represent these special type of binomial products, we'll have a look at their areas. Let's start off with some perfect squares. So if I have a rectangle that is x plus a on one side and x plus a on the other side, then it has to be a square, right? So I can represent the square in the top left as x squared, and then right next to it, this is a times x. And continuing on with FOIL, we end up with another ax. And this also has to be a square with side lengths a and a, right? So that's a squared. I think I've messed up the colours of FOIL. I was trying to be consistent there. But anyhow, hopefully you understand what I was doing. But that should be pretty easy to understand, right? But if we were to look at difference of perfect squares, notice the acronym, we're not going to find this as easy. But the way I like to do it is think of a square the size of x, and make sure you realise this whole side length here is x, not some sort of semicircle, all right? And this side length here is b, and we subtract that from the square of x. And so we've still got this area here. Then if I was to draw a rectangle on the side of this square that is the length of b, this weird looking shape is actually x minus b times x plus b. And this side here is x minus b, and this width here is x plus b. So therefore we have that rectangle. So if I was to redraw that square over here, and these two are obviously related, and put that rectangle b inside that, and then colour in the area of x we already had coloured in, we've actually coloured in the whole of the square of x, except for this little bit here. And this area has to be b squared, so therefore we end up with x squared minus b squared. And because the colouring on the left is x plus b times x minus b, and that has to be the same area as the x squared minus b squared. So we've shown it with area and with algebra. But as I said, you can take it to the bank that expanding binomial products of difference of perfect squares or perfect squares has an easy answer that you could skip all the FOIL steps for. We've almost finished the introduction, but I just want to make a note before we move on. While it's not 1000% relevant to this unit, it should be known that perfect squares and difference of perfect squares are really handy with numbers. For example, we know that x plus b squared is equal to x squared plus 2xb plus b squared, right? Then to use 15 squared as an example, well, that's just 10 plus 5 squared. And so following on with what we know about perfect squares, that has to equal 10 squared plus 2 times 10 times 5 plus 5 squared, which is 100 plus 100 plus 25, which is 225. And because x plus b times x minus b is equal to x squared minus b squared, so then 17 times 13 can be represented as 15 plus 2 times 15 minus 2. And using our difference of perfect squares rule is equal to 15 squared minus 2 squared. We've already figured out 15 squared and we all know what 2 squared is. So therefore 17 times 13 is 221. And I'll leave that for you to check with the calculator. All right, let's end the introduction there. I'll see you in the next section. You should consider this section and the pre-learning for it as a very gentle warm-up. Other parts of this unit will get quite difficult. So all you'll need is to recall the distributive law, i.e. a times b plus c is equal to a plus b times a times c, and recall collecting like terms. Of course, you better be sure that you understand what like terms means. Exactly the same unknowns raised to the same powers. Anyhow, let's get on to example 1, where they want us to expand and simplify the following expressions. In part A, the expression is minus 3 times x minus 5. So the only potential pitfall here is the negative times negative. But if you use brackets like this, that probably seems like an extra unnecessary step, but it might be helpful for some of you. Anyhow, taking into account the negative times negatives, etc., we end up with minus 3x plus 15. Alright, with part B, we've got 2x times 1 minus x. So 2 times 1x is 2x, and 2 times minus x is just minus 2 times x squared. Now we could have taken the extra step there with the negatives in brackets, but hopefully you're confident enough that you don't need to do that anymore. So moving on to part C, we've got 2 divided by 7 times 14x plus 3. So obviously we multiply both elements in the binomial by 2 divided by 7. And because the 7 and the 14 cancel out a 7 each, we're left with 2 times 2x, which is 4x. And there's no cancelling with 2s, 3s and 7s, so we're left with 6 on 7x. Not x, just 6 on 7. So the expression at the top, 2 on 7 times 14x plus 3, is just equal to 4x plus 6 on 7. Alright, and finally in part D, we have this long expression x times 2x minus 1 minus x times 3 minus x. And expanding the expression on the left, we get 2x squared minus x. And taking into account the negative sign, the expression on the right gives us minus 3x plus x squared. And the final step is to collect like terms. So we're left with 3x squared minus 4x. Alright, so that was pretty straightforward, I think. This should take you no time at all. You don't need to do all the questions in the examples, just enough to feel confident. So pause the video now and do questions 1, 2 and 3 in the new book, or questions 4 and 5 in the old book. And then I'll see you in the next section. Before we go ahead with the example, let's restate what we covered in the introduction. So for binomial products, we use FOIL. So for example, x plus a times x plus b, well, that's equal to the first, the outside, the inside, and the last. And when we collect like terms, that becomes x squared plus b plus ax plus ab. And don't forget, we need to keep our eye out for perfect squares and difference of perfect squares. Because with perfect squares, like x plus a squared, we know that's equal to x squared plus 2ax plus a squared. And for difference of perfect squares, like x plus b multiplied by x minus b, well, that's just equal to x squared minus b squared. Okay, so with those in mind, let's move on to example 2, where we're going to expand the following. So for part A, we've got x plus 5 multiplied by x plus 4. So using FOIL, we get the first 2, which is x squared, then the outside 2, which is x times 4 or 4x, The inside 2 is 5 times x. Finally, the outside pair is 5 times 4. And 4 and 5 are like terms for x, so we end up with x squared plus 9x plus 20. And the shortcut here is, if you recognize the 4 and the 5, then if you think about some of the algebra expressions I used earlier, particularly introduction, you could see that we end up with x squared plus 4 plus 5x plus 4 times 5, which is x squared plus 9x plus 20. So I typically just do this one in my head. Okay, part B, we have x minus 5 squared. And because it's a perfect square, I can write that out straight away as x squared plus 2 times minus 5 times x plus minus 5 squared. Therefore, x minus 5 all squared is equal to x squared minus 10x plus 25. So it's worth noting here that while x plus a squared is equal to x squared plus 2ax plus a squared, but if you've got x minus a squared, you end up with x squared minus 2ax plus a squared. All right, finally, part C, we have 2x plus 1 times 2x minus 1. Because the elements on the left are the same and the elements on the right are the same, and we have a positive and negative sign in either one, we end up with the difference of perfect squares. So I know that this equals the first element squared minus the second element squared. And 2x squared is 4x squared, so we end up with 4x squared minus 1. But make sure you don't make the mistake of 2x squared is equal to 2 times x squared. That is naughty. All right, well that seems plenty easy anyhow, so why don't you pause the video now and do questions 4 and 5 in the new book and questions 6 and 7 in the old book. And then hurry back and I'll see you in the next section. So as the binomial products get more complicated, make sure you stick to FOIL. But don't forget to keep your eyes open for perfect squares and difference of perfect squares. All right, let's move straight into example 3, where we're going to expand the following expressions. In part A, we've got 2x minus 1 multiplied by 3x plus 5. So the two first ones are 2x and 3x, and 2x times 3x is 6x squared. Then the two outside ones are 2x and 5, which multiplied together gives us 10x. Then the two inside ones is minus 1 and 3, which becomes minus 3x. Don't forget the minus sign there, okay? And finally, the last two are minus 1 and 5. And when multiplied together, that's minus 5. So the only like terms here are the 10x and minus 3x. So 10 minus 3 is 7. So we're left with 6x squared plus 7x minus 5. All right, let's move on to part B, where we've got 2 times x minus 3 times x minus 2. We can multiply in any order we want because of associativity, right? So I'm going to say 2 times the products of the binomials. And we end up with x squared minus 3x minus 2x, and minus 3 times minus 2 is positive 6. Collecting like terms makes this 2 times x squared minus 5x plus 6. And when I multiply the 2 through this trinomial, we end up with 2x squared minus 10x plus 12. And done. All right, let's move on to part C, where we have 2 binomial products. The one on the left is x plus 2 times x minus 4. And we're going to subtract the other binomial product of x minus 2 times x minus 5. And sorry, I'm not sure if I read it out right, but I've certainly written it wrong. That binomial product on the left should be x plus 2 times x plus 4. So hopefully you practiced enough to know how to just expand straight away. We've got a plus 2 and a plus 4x, so that's 6x, and 4 plus 2 is 8. So the product on the left is x squared plus 6x plus 8. And subtracting the other binomial product, we've got a minus 2 minus 5 is minus 7x, and minus 2 times minus 5 is 10. So we're left with x squared minus 7x plus 10. I'm not forgetting this is a minus sign. The 2x squareds cancel out. We end up with 6x minus 7x, so that's plus 13x. And 8 minus positive 10 gives me minus 2. So the subtraction of those two binomial products ends up being 13x minus 2. Big and complicated maybe, but really that's pretty simple. So right about now you should be pausing that video and working on questions 6, 8 and 9 if you got the new book, or questions 8, 10 and 11 if you have the old book. And when you come back, we'll summarise this lesson. I realise that this lesson will be very easy revision for most of you, but being confident with expanding is really important for factoring, which is going to be the big challenge of this unit. So coming out of this lesson, a successful student will review how to apply the distributive law to expand brackets, be able to expand binomial products, including perfect squares, and finally, be able to form a difference of perfect squares by expansion. So hopefully you've finished all your pre-learning already. It might not be a bad idea to get other questions done before class. Either way, I'll see you in that next lesson, whether it's in class or in the next video. Bye.